today Adam is here Adam's only here today. We're going to be heading out to Keck after Thanksgiving for some observing time. Introduction is PhD at Caltech with Lynn Hillenbrand. Then he moved to the IFA at Manoa as a Hubble Fellow, and then he moved for 1 year as a Clay Fellow at the CFA in Boston. And then ever since then, he's been a professor at UT Austin, which some of you know, I moved here from there. So long-time collaborator. I guess that's all the introduction you need.
Sure.
Oh, I see you're not wearing slippers, actually, which is very strange. When you were in Hawaii, you picked up an affinity for slippers and
yeah, I debated that.
So.
The slippers are nearby. They might go on after I finish doing the talk, but okay. Thanks, Trent. So today I'm talking about a project that I and my collaborators here, including Trent, who will feature at the end of the talk and some of the follow-up directions that things could go that are very exciting. So for as 6-ish years now, we've been working on this project to look at what the impact is of having a stellar binary companion on the occurrence rate and eventually the properties of planetary systems. We're trying getting hints as to how the planet formation process works, and also just thinking more directly, where do we expect to find planets? Where do we expect to not find planets? And how can this inform our knowledge of the star and planet formation process? Okay, so to motivate this, then I like to start with this figure that I think is an updated version of something I first saw shown in an 80s era National Geographic, which is a map of the solar neighborhood. These are the stars out to presumably 5-ish parsecs, judging by the names of the stars on the edges of the figure. But the specific stars here, for the most part, aren't really that important. The thing you want to take away from this is how many of them are not by themselves. If you look around us in the solar neighborhood, you have a lot of binary systems, triple systems, quadruples, etc. Even the very nearest system is actually Alpha Centauri, A and B, and Proxima floating around presumably somewhere in this figure. And yet, if you listen to the story of finding exoplanets, of studying planet demographics, of the entire planet formation process, then it typically only has one star in the middle. The planet assembly process is going on around it, and we don't really think about having other complications there. But it seems like the majority of all solar type stars are formed in binary systems, and even to the present day, most of them are still living in those binary systems. And so we need to be thinking not just about the story of one star, one planet, or maybe multiple planets, but it's one or more stars, one or more planets, or maybe 0 planets, to spoil maybe where this might be going. And really, I think the reason that most studies of planet formation have concentrated on the one star and then some planet story is just because once you add another star, things get very complicated. In particular, you get a very depressing litany of all the reasons why you don't expect to have any planets. And I'm going to run through them sort of in chronological order of where they fall at, and then summarize it in about 5 slides. But obstacle number 1 is if you have another star there, you expect to be sculpting your protoplanetary disk. So this shows some of the early simulation work of what happens if around the center of mass of a system, you have a planetesimal disk. Then instead of just having one star in the middle, you have 2. You ask, how do those stars tightly interact with the disk? And what you find is that if it's a binary system internal to a disk, you truncate the disk inwardly out to about 3 times the binary semi-major axis. And if it's another star outside of the disk, you truncate it outwardly down to about 1/3 of the semi-major axis. So here's obstacle number 1. If you don't have any planetesimals there, you're not going to form any planets there. And so you have a restricted range of so you have a restricted just range of locations where the planets can format to start with. But even modulo that, you also have to worry about, well, you've been tidally truncating, you've been stirring, etc. Does the presence of that extra star and do the tidal forces that arise from that end up stirring the disk enough that it inhibits the assembly process. Basically, the idea is if you have one star and the planetesimals around it, for various reasons that you can ultimately trace back to das drag and coupling of small particles to the das, then interactions tend to be relatively quiet. Things are drifting together. They're not colliding destructively. And so when you get things intersecting and colliding, they accrete. And so you build small stuff into big stuff. But if you're tidally stirring up the planetesimal disk, then what instead happens is you are knocking planetesimals onto eccentric orbits, onto inclined orbits, and they're going to have higher collision velocities, which means that for a larger fraction of collisions, they're going to be destructive, not constructive. Instead of growing small things into bigger things, you're going to take whatever things you have and grind them down to even smaller sizes. Not planet assembly, but boulder destruction, pebble destruction, etc., which is shown here in terms of a model of a bunch of planetesimals in an external planetesimal disk around a fairly close binary system, where the red are interactions. So this is impact velocity versus the orbital radius of the planetesimals. This was trying to specifically assemble one circumbinary planet found by Kepler. And if you didn't account for the stirring, then you would get these collisions where red is accretion, black is erosion, and most of the collisions end up down here in this low velocity band where things accrete. But if you stir it up, then things end up being stirred to higher impact velocities, and so most of them erode. So there's number two. Even if you've got planetesimals there, you might not be able to build anything out of them. Obstacle number three is that you probably are getting rid of your disk quickly. So even if you have stuff there, you probably at least have a shorter time scale to build your planets. And this can be pretty straightforwardly justified just in terms of those tidally truncated disks, especially inwardly truncated. Though you could also make a similar story for having a binary outside of the disk. Because if you're removing the inner part of the disk here, then what happens for a single star is the high energy radiation from the star, the UV, the X-rays, come in and mostly hit the inner part of the disk, where they can heat it up, but they don't heat things up to be above the escape velocity. So you might like heat it up, things get a conveyor belt, mass will flow out here, ultimately come back to the disk because it's not unbound from the system. And you might get a conveyor belt going on, but the mass stays. But if you put a binary star here and truncate it like here, then things are high enough up in the potential well that you just photoevaporate the disk material straight out of the system. Stuff just flows out and goes away. And you should fairly rapidly destroy your disk. And I'll talk about some results that seem to show maybe this happens really quickly in a little bit. So fewer places to build your planets, harder to assemble them, less time to do the assembly. And then number four is even if you manage to assemble planets, then if you do long-term in-body simulations, you find that very few of them are actually stable over good year timescales. So this is one of the early simulations for Alpha Centauri asking where could there be stable planets. So they put down a bunch of planets given the known orbit of Alpha Centauri A and B, and then ran it forward for a while and asked what stayed. You basically get the points here. So around each star, you have planets that survive if they're inside of an AU or so. And then outside of it, you have to push things out to 100 AU or more. So the scale here is 0, minus 100, plus 100 on the right. And then basically minus 30 over here, the plus 15 on the left. So even if you manage to form them, then they might not last. So this litany seems to suggest that it's actually, you shouldn't really expect to find planets in binary systems. You can kind of summarize this maybe before we move onward, just in terms of a timeline. So for the star formation people, you will recognize, having seen hundreds of figures like this. This one was made by Andrea Sella for his thesis. If you want to think about this in terms of the time scale where all of these processes are happening, then you put it in context of the class 0, class 1, class 2, class 3 protostars, where basically mass is in the envelope, but you've got a star, recognizable star-like thing in the center. Most of the mass is in the star in the center, but you still have an envelope. You've got a protoplanetary disk, no envelope anymore. And then you've gotten rid of the disk, and you basically just have planets and maybe debris, second generation dust produced by planet collisions. Then these will happen sort of through here. Disk truncation is in the, sort of these stages. Planetesimal stirring is sort of class 1-ish onward. The evaporation specifically sets when you go from class 2 to class 3, when you get rid of your disk. And then the ejections are down here at late stages. And so the question you want to ask is, once we figure out what is the planet occurrence rate at the end of this, we want to be able to ask which of these stages is actually what's limiting binaries from having planets. So we can think about this in terms of where can we look at the planet occurrence rate, or at least planet indicator occurrence rate, in order to try putting some limits on what is going on to allow planets to survive or not. I'll be specifically talking about two stages, the protoplanetary disk stage and then old planetary systems at the very end of all of this. But you can also think about this at very early stages, or maybe just after you've gotten rid of the disk in terms of debris disk occurrence rates. We'll concentrate on these two for today. And the reason that we're concentrating on this is, despite this very depressing litany, we find planets in binary systems. So clearly this is not 100% binaries are terrible, never look for planets there. But it does seem like things are, we expect something, but people are finding planets all the way back, I think, depending on how you want to argue about it, Gamma Set, one of the first planets where at least its influence was detected, even if it wasn't really called a planet for quite a while afterward, all the way up to quite a few Kepler systems, circumbinary planets in Kepler, and also visible binaries where there are transient planets are in one star or the other. So it looks like this does happen, but up until now, it's been hard to get statistics out of this because these are out of bias surveys. And basically the problem is, once you have two stars there, then observationally, it gets hard to find the planets. But then also, once people know that there's a binary there, they also tend to sort of drop them out of their planet samples. And so you've got these two effects here going on to make it really hard to just make a histogram of what is the binary semi-major axis distribution for planet hosts, or what is the just planet occurrence rate in binaries versus singles. Because when you see that it's a binary system, it's very hard to then do that comparison of the singles versus the binaries. But okay. So to summarize the intro and to set us up for going forward, basically, there are good reasons to expect binary systems to be hostile for planets. But the question is how hostile, or hostile at all. The universe really seems to enjoy doing things we say it shouldn't do. So never end with the theory and say we're all good. As an observer, I will say we should go observe. It's hard to find the planets in binary systems, so it's been hard to quantify this. But I would argue the key here is it's easier to find binaries. And I'm a big believer of doing the easy thing if it answers the question and not going and doing the hard thing just for style points. So I say, let's start with unbiased planet samples or samples of planet indicators, things that say there are planets there or could be planets there. And then look for the binary stars. Because stars are bright, they're easy to see. Trying to go and do any kind of planet search is always a long and difficult problem. So I'm going to talk about two programs today, one aimed at early times, one aimed at late times, that are meant to do this. Say we have some indicator there are planets there, or you could form planets there, and then let's go look for binary systems among those. We didn't know about them beforehand, so there's at least a limit on how much they can really bias us. There are still biases we're worried about. And then let's look at the statistics. So I'll start with one looking at protoplanetary disk hosts and looking at their binarity. To remind you, then the census of young stars in nearby star-forming regions is actually getting pretty good. And a lot of this is due to Spitzer giving us complete maps in the mid-infrared of all the nearest star-forming regions, where you can go and very easily say, this star has an infrared excess. Let's go take a spectrum just to make sure it's a young star and not something weird, some post-mean sequence thing or contaminated by an AGN or whatever. And then you've got a young star with a disk. And so we have hundreds to thousands of stars we can go look at as saying planet formation is ongoing. There is an optically fixed protoplanetary disk there. What are the properties of the star? Is it single or binary? There's a caveat here that the star formation people should be already thinking about, which is Spitzer told us what has a disk. It doesn't tell us what doesn't have a disk. And this is actually something my group is working on, is finding what are the stars, even very young stars, that don't have disks, because I think we're still missing a lot of them. But this at least gives us a good handle on what are the young stars that might currently be forming planets. And so we can use those disks as a proxy for planets. They could have the opportunity to make planets. Once the disk is gone, they'd better have already finished planet formation, or else it's going to be really hard to get planets later. The problem is that these regions are relatively far away compared to the nearest field stars. So the nearest ones that I spend a lot of time studying are Taurus Auriga, Upper Scorpius, Helion, somewhere around in there. They're all named after the constellation that they're in, but they're all at 150 parsecs or more. So to calibrate you, then for Alpha Centauri, a 10 AU binary to pick a scale that is the Alpha Cen AB semi-major axis, and a scale that is solar system size, is 8 arc seconds. That's not hard to see. If you want to go to someplace like Taurus, that corresponds to 0.07 arc seconds. So it's lambda over D in K-band on 8 to 10 meter class telescopes. So close binaries are hard to see. And so this is setting us up for a technical challenge. So I was listening earlier, binaries are easier to find than planets, but you do still have to struggle with this. And specifically, the binary census has been slow in these nearby star-frame regions because we need higher resolution to just see the binaries. So this is the basically demonstration of what does the atmosphere do. We're at an observatory. I think we're all very well aware of what the atmosphere does to our observations. But if you blur out, if you have a binary system like this and run it through the atmosphere, you get that due to the turbulence in the atmosphere. When your telescope should see that, or really here, it still isn't perfect correction, even though it's behind AO. And so what we want, what our telescopes would show, if not for the atmosphere, is this. And even then, the things we're looking for aren't even like this. We're looking for that and another star out of the first null or inside of it. So we're really pushing the resolution limit. And so there's two solutions, or two parts of the solution on how we can find these close-in binaries, where even for the nearest star-frame regions, where we have to go to lambda over D to see binaries that are orbiting on solar system scales. Part one, we all know about for the most part, is using adaptive optics. Idea being, the light coming in from that distant star is a planar wave above the atmosphere. You run it through the atmosphere. It's basically like a bunch of phase screens, a bunch of lenses due to having different pockets of turbulent air that deform it, and you get a corrugated wavefront by the time you get to your telescope. Bounce the wavefront off of a deformable mirror that you can push parts out or pull parts in to change the path length, and you can get a planar wave out, send part of it to your camera, send part to a wavefront sensor that then tells the deformable mirror how to update in time to keep up with the atmosphere. So that in real time, instead of getting an image that looks like this, you can match it with a deformable mirror that looks like that. Change your wavefront to look more like this and get a nice differential image out. And this is great. Using this as an example, if you've got your star here and you want to find something out here, out several times past the differential limit, then this is great because you just look and say, there's something there. Do I see another point source here? Yes or no? Done. But getting that stuff inside of the first area range, inside of the first null, is really hard here because the atmosphere and the optical imperfections of our telescope and everything else are basically continuously changing the shape of the differential limited core by small amounts. And it's really hard to calibrate that. Like out in here, you can use angular differential imaging, spectral differential imaging, etc., to say, am I seeing an artifact, a speckle, or a real companion? In here, none of those work. The rotation's too low, the wavelength dependence of the angles is too small, etc. So the solution part two for me is to use interferometry. And specifically, this is called non-redundant masked interferometry or aperture masked interferometry. There are like 5 different names floating around. We really need to standardize our terminology. But the idea is, if you normally had a telescope and a data system and stream cartoon view, your telescope makes an image, you put your camera here at the focal plane, and you get an image of a diffraction limited star. But here, the problem is that there are speckles that you can't necessarily distinguish from companions, and you have the same issue of small changes in the PSF shape in here could look like spurious companions. So what we do is we take the light from that, and instead of just making an image, we pass it through, at the re-imaged pupil plane, a mask that blots out most of the light, blots 90 to 95%. But it passes light through specific places to create baselines that are only present once. And then what happens is when we bring it back to the focal plane and make an image, we don't get the star, we get the interferogram of that starlight going through those 9 apertures and interfering with itself. It's the 9 aperture 2D version of the 2-slit experiment that we all did in physics labs as undergrads. And the key is, specifically, because each baseline is only represented once, the interference patterns in here can be uniquely tied back to what is happening on these different baselines. So it can tell you what is going on with the phase of the incoming light going through each of those apertures. So we can do things like screen out the phase errors that cause those speckles. Sort of in cartoon view, maybe, well, in view of taking someone else's figure, showing how this works for a full frame speckle, and then demonstrating the aperture mask equivalent. If you have just an image and you take a Fourier transform of it, then you end up getting the Fourier, in the Fourier plane, amplitudes and phases of your Fourier transform will look like this. And this is how speckle worked since the 90s, 80s, maybe is when speckle first started really being used, where you would just take very, very short frames and freeze out the atmospheric turbulence. And then you would be able to see this. With AO, you don't have to take the short frames. You can still Fourier transform an AO image if you want and get this. So what we're doing is by introducing that mask and seeing the interferogram, then we're basically getting the interferogram of the light from those two stars going through the apertures and interfering. And then we Fourier transform that. And we're getting this phase and amplitude information from the complex visibilities, but we're getting it at specific places, each of which could be traced back to one of those baselines, one of those pairs of apertures. And then what we can do is construct what we call closure phases. So we can say around a triangle of baselines, if you construct the phase sum, then any phase error on one of those apertures that is not astrophysical, that is not tied to the scene on the sky, and hence common to all of them, is going to cancel. So if this is the interferogram, these are the visibilities, you measure the phase sum here, here, and here, which you can trace back to this baseline of apertures in your mask. And then if you have some phase error specifically on one of them, and the cartoon view from back when this was first suggested in the 80s is you have some positive turbulent atmosphere over one of them. You might introduce a positive phase error on this baseline. We'll introduce a negative phase error on this baseline. So on the sum, that cancels out. Basically, what this is doing is making a very weird looking PSF that has calibration properties that are very stable and are independent of most of those phase errors. And so then we can go digging really deep, really close in. So contrasts of 6 or 7 magnitudes at the differential limit in K-band. And we even get a couple magnitudes at a third of the differential limit in K-band. So this is what lets us get those binaries that are close in. All right, I'll just stop as an aside. So I'm talking about binaries today. This can also be used for doing like planet searches. So this is one of my other results that I've had out of this, where if you do a deep observation of a young star going for hours, you can potentially even get to the planetary mass regime and see protoplanets or planets in the process of being assembled. But my planet formation talk is a topic for another day. But this is 76 milliarc seconds. So there's a star here, there's a point source there in K-band, and L, we can see spatially resolved stuff around it. And for the last 5 years, I think people have been arguing over whether we have 1, 0, or 4 planets in there producing all this flux. I don't know the answer though, so I'm not going to dwell on this today. I'd rather talk about binaries. Okay, so we've used this for binary surveys of young stars for hundreds of stars now. I think the over 400 is probably obsolete. We've added more since. Observing young stars in near circle regions with imaging and with non-redundant masking. And this shows really the key of why this works so well. So this is a plot of contrasted magnitudes, 0 down to 6 or 7 down here, versus separation in milliarc seconds. So here's 100 milliarc seconds. Lambda over d on Keck is going to be here, and we're getting 4 to 5 to 6 magnitudes of contrast, and these were relatively quick observations, 15 minutes per star. And if you go to a young star where even low mass things are bright, this turns into at about 5 to 7 AU, limits that are in the 10 Jupiter mass range or below. We originally did this because we thought if there are high mass super Jupiters, we could detect them. Looks like there aren't, but we did get a ton of binary systems detected in the meantime. And so, since we didn't find any planets really with this technique, well, found one in a later, even deeper survey. Our snapshot survey didn't find anything. We found tons of binaries. We started doing science with those. It's the story of direct imaging planet searches. You look for planets, you don't find them. You say you do binary science, and then you make the papers.
Or brown dwarfs.
Yeah. And so what we did is, as one of our first steps was, we said we have all these binary star systems, and we have single stars let's look at what the disk frequency is from the Spitzer observation. So here it's disk frequency from 0 to 100% as a function of the separation in AU, splitting them up into bins of order 10 to 15 binaries per bin. And a result immediately jumped out to us. Inside of about 40 AU, then the disk occurrence rate for close binaries was something like a third. Outside of that, it jumps up to 80 to 90%. You look at the single stars, it's floating somewhere around 80%. So you have this story that looks like once you're inside of about 40-ish AU, you can probably move that a line by some amount one way or the other, then you have about a suppression of a factor of 2.5 to 3 in disk occurrence compared to the wide binaries or the single stars, where it's consistent with everything basically having the same probability of having a disk. So there's one observational indicator that by an age of a couple million years, then these things, we can't say they don't have planets, but they better have made their planets fast, or else they won't have a chance to make them, even while all the rest of the stars that have the disks can keep on assembling things and turning small stuff into base. Which actually has an interesting corollary as well that I like to point out, which is people like to make these plots for single or for all stars of disk frequency versus age in millions of years. And so the story has been at early times the disk fraction's high, at late times the disk fraction's low. There's sort of a linear decline here. But for example, in Taurus Auriga, where I made that figure, if you take out the binaries where it looks like they've gotten rid of their disk early because they were binaries, and just look at what is the disk fraction for single stars, you actually revise it upward a lot. So people would say in Taurus, the disk fraction is 2/3. A third of them are already done with the planet formation. But most of those that are done are binaries. Because for the single star specifically, you can rise it upward and say it's somewhere in the vicinity of 80 to 90%. And so we're not just talking about binaries here. There are implications for single star planet formation too. And really, if we take this and play the game in other places too, it looks like this effect gets baked in very early. So here's a plot of the disk frequency inside 40 AU. So grouping together all those bins as a function of age for several nearby groups where we have enough AO observations, enough mass observations to find binaries. And you actually find that the disk occurrence rate is in the 30 to 40% range, even by an age of 1 million years or less. So by the time you get to a few million years, it's still in there. Then by the time you get out to 5 to 10 million years or beyond, then it's dropped a little bit. But for as the unknown populations as we can look at, then the disk fraction in these close binaries is never 80%. Which raises the question, how early is this baked in? Maybe they never had a chance to form planets. I'll just add one more note before we move onward. There also has been parallel work on disk masses by, in this case, Robert Harris, where he looked at the same binary census that I'd assembled and didn't just ask binary or ask protoplanetary disk yes or no. He said, what is the mass of the disk as measured from the submillimeter flux, which is a decent proxy for dust mass, which he then turned into total mass. And he actually found an even more striking trend, which is if you look at the flux from the flux in the millimeter, which is a proxy for disk mass, as a function of binary projected separation for a bunch of systems. And then the single stars are over here. Basically, the singles have this distribution. Outside of a few hundred AU, it's indistinguishable. So you have as much mass budget to make planets in these wide systems as you do in the singles. If you go inside of a few hundred AU, at 50 to 500 AU, it looks like you suppress this whole distribution downward by about a factor of 5. And then go inside of 50 AU, and you suppress it downward by another factor of 5. So you have 25 times-ish less mass in here than you do for single stars or wide binaries. Even though this doesn't even include the things that we know don't have disks. These are only things that we see there's an excess. We know there's some kind of disk there, and it's just getting a mass for it. And so Robert's results here show that it's not even just a time scale limitation. It might also be that the presence of the binary is reducing your mass budget by a lot, which will, I think, make for a weird figure for me to talk about later on when talking about old planets. But this is all a little indirect. I'm using the presence of a protoplanetary disk around a young star as a proxy for there could be planets later. But all I'm saying is there could be planets later. And even if there's no disk there, maybe there are already planets. So there's some combination of planet occurrence timescale and planet survival timescale more generally that can get involved with this to confuse things. So really, if we want to know a final boundary condition, after all those processes are done, do the planets survive or not? You should go look at after all those processes are done and ask if there are planets there. And so this is the other program I'm talking about, which has been going on for most of the last 5 years and is still continuing in various follow-up programs. And to do this, then we're taking advantage of the other big sample of planets or planet tracers that isn't really that biased by the presence of binary companions. And that's the Kepler sample. And so specifically, well, I've got my movie of a transient planet here, but don't need to dwell too much on it. Because we basically know some nearby binaries do host planets. For example, Gamma Set. But most searches are forced to anti-select against close binaries because, like for RVs, if you have 2 stars there, you're not just trying to sort out what is the spectrum of one star doing to 1,000th of a pixel in your spectrum, so you can measure the velocity down to meters per second. You're also trying to figure out what is the other star doing as they're both orbiting around each other. And so your detection limits get really bad really fast. And so if we don't want to deal with this, we should go to a sample that was selected without knowing whether they were binaries or not, and where things just are never spatially resolved, so that the presence of the binary can never make it that hard to find the planets. And there are some caveats in that. The binary does make it maybe harder to find the planets, but the trends to make it harder versus easier more or less balance out, which I can get into later if people want. So Kepler has found thousands of planetary systems since 2010, and none of them were selected specifically because this is a single star, and so it doesn't have that potential bias baked in. And these thousands of planets provide a good sample to go do a binary survey and ask which of them are binaries. So I can probably more or less skip past Kepler results. I think I had this for when I gave the talk at a physics department, and I wanted to remind them transient planets, what they are, et cetera. But so our survey here was, once again, use the same techniques, use the same telescope in order to go out and look at planet hosts. And to date, our sample is up to roughly 500 of them, going out to about 500 parsecs. I think we've added a few more since I picked this 430 number here. And specifically, we're in a snapshot mode, even more snapshot than we were for the young stars, because we knew going in we needed hundreds of targets in order to be able to dice up our sample into binaries versus singles, divide along semi-Draxis, divide along mass ratio, divide along primary star mass if we can, et cetera. So we've really been getting in and trying to figure out how to make this as fast as possible. So it's basically 7 to 10 minutes per target, and we've been able to basically go in and stripped up new observing sequences for NERC2 operating at the instrument level to get imaging, chronography, and aperture masking all for every target in those 7 to 10 minutes. That's 10 minutes with laser guide star AO. So it's a fast-paced observing night. But when our survey is cranking along, we're getting data that looks something like this. So this is our observations using NERC2 on Keck for KOI1, which was the pre-known transient planetary system TRACE2. So we basically get 2 images, just quick snapshots to tell us where the primary star is at. We then have a script that grabs this primary star, moves it behind the chronograph, and takes another couple of images with much more Fowler sampling so we can get really faint companions. So here we're getting the contrasts of 7-ish, 7.5 magnitudes in K-band. This lets us go down to 10 or 11, basically get to the sky background limit for most cases. Then we move the chronograph out, move the aperture mass in, and get 6 to 8 interferograms like that we can interpret. And here you can see it had a known relatively low mass binary companion that was identified beforehand, but we see it in the imaging, we see it very clearly in the chronography. We even have aperture mass interferograms of that as well. So we can ask if it's a binary, if it should matter for anything. Okay. And so we did that for hundreds of stars, and we basically ended up getting a giant stack of detections and detection limits. And this shows get a little deeper into figures like the ones I showed before of what we did. So this shows our detections, which are the X's, and then the contrast in KMAC, and then the detection limits, of which the median detection limit is the orange line. in terms of delta K, so the contrast in magnitudes at K band versus the separation in milli arc seconds. So here's 1 arc second, and then the dynamic range here is basically from 0 down to 10 or 11 or 12 magnitudes for the very deepest chronographic images, which is basically the brightest primary stars behind the chronograph. And to really emphasize the advantage of aperture masking, if you were just doing imaging, you would basically get something like this, and then you would merge in with things here, and then it would go up like that. You'd basically get equal brightness binaries at the differential limit at 15 milli arc seconds. So this slice here is what you get from doing the aperture masking. And then the chronography lets you go from here-ish on downward, arbitrarily faint. It's mostly useful for identifying very high contrast background field stars, more so than binaries. If you want to do vetting, or vetting to get rid of like very high contrast tilting binaries that look like planet candidates. Okay, so these are all the things we found. We found hundreds of candidate companions to these nearby objects. It's worth adding as a caveat, these are candidates. We're working on common proper motion, but we haven't gotten that yet for all of the sample. But the thing to point out here is, and this is one of the advantages of doing this in the near infrared, is the contrast to get to relatively low mass binary companions is not that high. So go 2 magnitudes in K-band from a solar type star, you get down to something that's 0.6 times the primary mass, 0.6 solar masses. 4 magnitudes gets you to 0.2 solar masses, and 6 magnitudes gets you to 0.1. So we're basically getting, since binary masses are sort of uniformly distributed, binary companion masses, then we're getting 80% of the binaries all the way down to here and all the way inward to inside the differential limit. If you turn this into something that's easier to parse in terms of what we expected from the binary population, we can plot this instead in terms of derived quantities. Turn the contrast into a mass ratio. So this is secondary mass over primary mass from 1 down to 0. And then separation in AU, taking into account the distance to each star in order to convert the angular separation to a physical separation. And then this is 10 AU, 100, 1,000. Our touch limits go inward to something like 3 AU, 3-ish, and a little under 3 for the median target for equal brightness binaries. We're still getting inside of 10 AU, all the way down to mass ratios of 0.2. And then the x's here are showing all of those candidates. And here we're not, and there are upper limits here for the things that are below the bottom of our models that we're using. So basically under 0.1 solar masses. And this is assuming everything is bound. You'll notice there's this giant cloud down here. Those are mostly background stars where we can't say they're background yet. We're working on that. So we just throw them in here. But if we want to do statistics, we basically have to work with a box that's something like this in order to avoid all of those background faint distant stars. Okay. So we have a bunch of companions, many of which we think are real. And we have detection limits, so we can say, where should we have expected to find companions, perhaps, that we didn't? So in order to interpret this, we run simulations of the known binary population we see in the solar neighborhood. We just ask for the stars that we observe, for their distance away from us, for their and for the detection limits we got for each one, also baking in Malmquist bias and Malmquist bias. So we expect to see binaries overrepresented because they're brighter, and so they're more likely to slip into the sample. Where should we have expected to see binaries? So that's the cube helix colored image underneath of all those X's. It's the same plot, mass ratio versus separation AU. And the color here shows the density of X's you should expect. So where it's white, there should be a sort of 16 per box, kind of like this. And then turning downward, the orangish is 8, the greenish is sort of 5 or 6, down to 0. So this is our detection limits where things are too faint below that. This is where the binary semi-Draxis distribution starts to tail off at wide separations. And then this is our inner working angle where contrast to the primary star is what's limiting our ability to find things. And looking at this, one thing that might jump out at you is that outside of a few tens of AU, then there's a fair number of things like out in here in the green and almost nothing in here. And up in here, there's plenty of X's in the white to pinkish area. But then even those kind of die off in here at 10 to a few tens of AU. So if you look at this, you can kind of convince yourself that it looks like there might be a deficit of these close-in binaries among the confirmed planet hosts. You can then collapse this down to a histogram in order to make something that's a little easier to interpret. And basically, that simulation of what we would have expected just from the known population of nearby binaries should have made this blue curve in terms of number of companions seen as a function of projected separation in AU. And the red is our actual data, where outside of sort of 100-ish AU, it seems to match up perfectly. You meet it inside of 100-ish AU, then it's suppressed by a fair amount. The histogram is undershooting what we should have seen for a randomly selected sample of nearby all stars. And so this is a pretty clear signal. I think it was 5 and a bit sigma was the final number we ended up at when you added together all of those bins. Now note there's no normalization here. This is just saying we know what the binary occurrence rate is around nearby stars, so that sets the normalization of this blue. And then the red is our data. So it matching out here hundreds of AU out to 1,000 AU is actually a very nice sign that for white binaries, looks like the binary population is doing what we think. But then the question is, well, it looks like there's a suppression of close-in binaries. Can we characterize that some way? And when I first made this figure, I said, let's make some really dumb toy model and say, inside of some cutoff, let's suppress the binary population by some amount and see what happens. And it actually turns out this dumb model makes things work pretty perfectly. So this is basically saying, I think here it was inside of a semi-major axis of 50 AU, the binary occurrence rate is 1/3 of what it is for wider systems or for the nearby field population. And it takes this close-in excess and drops it down by removing most of the close binary systems. It's not quite zero. Here, you have to worry about, there are some close-in systems that survive. There are some wide systems that are being seen close in projection in our observations. And sorting out which of those is which is actually going to take some legwork going into the future. But this toy model works pretty well. And specifically, sort of the punchline, sort of the average of both of those is saying inside 50-ish AU, 1/3 of binaries host planets compared to the fraction of single stars. And so we're doing, this is 20% of all the stars in the Milky Way. Because over half of all stars are in binary systems. And then this is about the median semi-major axis. So this is not a small effect. If you're not accounting for this, all of your planet occurrence rates are systematically off by 20%. In the era where we have thousands of planets and we're claiming to do precision exoplanet demographics, then this and many of the other systematic effects that people are starting to discover are actually what's setting our limits, rather than just the number of planets found. It is worth noting, because we can't distinguish something that's intrinsically short period, small orbit from something that is wide but seen close in projection as it orbits through at the time we're observing, then there is some degeneracy between these numbers. You can push your cutoff outward to say it's inside of 100 AU and then have a less severe suppression, so a factor of 2. Or you push it inward to 15 AU and have the suppression be 100%. And you end up suppressing about the same number of companions in our sample. You make basically an identical curve for either extreme. But the total number of systems that are missing is just taken by the difference between basically that curve and that curve. So, so the actual fraction of all stars that are affected is pretty robust. But, okay. There are a few interesting trends. Survival doesn't seem to correlate with planet multiplicity. So this is the ratio of singles to doubles to triples to quadruples among our sample, among the close binaries where the close projected separation binaries where they do have planets. And this is more or less not different from the wide binaries or the single stars. It doesn't correlate with super Earths or mini Neptunes, which is a little weird. I'll remind you of Robert Harris's result, where he found that close binaries had 25 times less mass budget to make planets, but they're still making plenty of super Earths and mini Neptunes, just like single stars, just like wider binaries. And there's no trend if I plot planet mass as a function of binary semi-major axis for the planets in my sample. We can't really say much about Jupiters because our sample is effectively volume limited and there just aren't that many Jupiters in there. Our sample is dominated by the common planets, not by the largest planets. And there's no trends with binary mass ratio either. Low mass binaries versus equal mass binaries seem to have the same effect. modulo multiplicity bias that we baked into our models. Okay. So this gives us a few lessons for planet formation, actually, because we've now set that final boundary condition. It now seems that if there's a binary companion solar system scales, it suppresses planet formation and ultimate planet survival by a large factor. It's not necessarily 100%. We don't look at individual systems where we know of orbits of the binaries and see there are planets there. So it's that suppression rate is not 100% with a very close-in cutoff, no matter what was formally allowed by my model. But it's at least 50%, probably 2/3 or so of the close binaries don't have planets, specifically because they are a binary system. But once you remove the binaries, the disk fractions at 2 to 3 meta-years are over 80%. And you can combine this with the sort of top-level conclusion that was drawn out of the full Kepler sample, where they said there's basically 1 planet per star, or pretty close to it. It was consistent with the vast majority of well, not all, but a large majority of stars in the Milky Way having planets. What this is actually saying is, the depressing side of it is to say the binaries don't have planets, but we're just moving around where we're attributing the planets that Kepler found. So this is saying the single stars and wide binaries actually have even more planets than we thought, because those are the things that all of those planets are around, rather than the close binaries. But the punchline here is, it seems like if the less than 50 AU binaries want to form planets, from the disk results, they better do it quick. And from the Kepler results, it seems like they didn't do it quick. And so something like 2/3 of close binaries fail one of these steps. We can't say which just from the Kepler results, but given that this matches up reasonably well with our results for protoplanetary disks, it seems like it's one of the earlier steps. And if you push it down to under 1 million years, you still don't have disks. Maybe the punchline is, at these young ages, you just don't have stable disks to build your planets out of pretty much ever. But there is sort of this open question, why do some close binaries apparently keep their disks and form planets? And so for the last few minutes of this, I'll go through some of the options of how we can try answering that question. And one of the places we're starting at is specifically measuring proper motions of the candidate companions to see which ones are co-moving with their host stars, which ones aren't, so which ones are background stars, because we'd like to be able to push to fainter binaries and dig them out of the field star contamination and push to wider binaries. But with sufficient astrometric precision, largely thanks to Trent over here, you can actually even address another question, which is not just are they co-moving, but to what extent are they not co-moving due to orbital motion? So this is one Kepler planet host system, KOI 3444, which has a bunch of faint stars around it and one pretty obvious binary companion. So this is a chronographic image to show all the faint stuff. And we took multiple epoch images spread across a few years and calculated the proper motions of everything with respect to that central star. And what we basically find, and then use that to turn into absolute values. And if you look at the proper motion diagram, so proper motion in right ascension and declination, all the faint things are basically centered around 0. And the black dots here are just a very wide swath of, I think it was USNOB or something, to show a comparison set of just distant field stars. But A and B both have about the same proper motion, but only about. B is actually different from A by something on the order of a few milliards seconds per year. And if you make a plot of this, and this is specifically what is the sort of position angularly versus the separation between them. So you think about this as separation and position angle. Over time, you find from 2014 through 2015 to 2016, then the separation has been increasing, but the PA has not. Which is an interesting statement that B is in an edge-on orbit, more or less around A. Which is interesting because A has transiting planets. The planets are in an edge-on orbit. So this looks like a case for orbital alignment. And Trent may or may not have shown this figure yet, but okay, well, look for Trent to tell you about this figure. It's really cool. But basically, it seems like a lot of things are aligned. Maybe most things are aligned. So they're interesting dynamics. But I'll try not to rain too much on Trent's parade and skip forward to some of the other stuff, because we can also play this game at young ages. So this is a plot of an orbit for a young binary system where it has a disk. So Rotzes 47 is in Ophiuchus, And we've observed it with aperture masking, and between 2009, 10, 11, 13, and 14, we have observed it to go through here. And you fit an orbit to that, and the orbit fits beautiful. The error bars here are smaller than the points, and all the points overlapped within the point size. And so we can go to these places where it's a close binary, it has a disk, and we can get a full orbital solution and not just say is the motion like radial or tangential, but what is the eccentricity? What is the inclination, etc. And this is a particularly weird one because the periastron distance is 1 AU. So when it's going through somewhere over here at periastron, the two stars are separated by 1 AU. And yet you still, and then out here, it's 10-ish AU. And yet you still have a disk there that you have an inner disk around the stars and then also an outer disk. And the disk has survived. If you'd asked me why do planets survive in some cases, I would have said circular orbits, everything well aligned, very dynamically calm. This is not circular, this does not look particularly calm. And yet there's a disk there. So we don't have a clear story yet as to why some of these binaries managed to form their planets. And finally, the last piece of this, looping back around to a caveat I listed near the start, we're also working on a new census of all these nearby star-forming regions to do a better job of finding the stars that have already gotten rid of their disks. It's hard to find them because if it has a disk, you look in Spitzer data or look in WISE, you see, oh, it's really bright at 3.6, 4.5, 8 microns, et cetera, 12 microns, 22 microns. If it's a young star that doesn't have a disk, it's just a star. There are a lot of stars in the sky. Figuring out which ones are the young stars spread over, in this case, 20 by 20 degrees for Taurus or Ida. Finding the few hundred young stars among many, many more than a few hundred not young stars is a chore. But we can use tolerant magnitude diagrams, proper motions, etc., to identify the candidates and then get spectra to confirm them. And basically what we're doing is going back and trying to ask, did we miss disk-free stars early on? So are there, and then once we have the disk-free stars, are all of those also binary systems? Interestingly, it actually turns out around the core of Taurus, so around in here and down in here, we're not finding that many more disk-free stars that weren't already known. The census was complete. But we are able to go further afield and go out to like the periphery. And so this actually started out as testing whether we missed the disk-free stars in the original surveys. It's turning into the original surveys just were a little too parochial in terms of saying, oh, Taurus is this. When it actually looks like this whole star-forming region has been spinning off stuff for a while, and it spans a much larger area. But we'll be able to update those statistics and get a better estimate of what fraction of stars have a disk or don't. I just skip over model upgrades. Nobody ever likes to hear about pipeline upgrades. And I think I'll just wrap up here with the punchlines, which are basically the ones I already said. When there is a close-in binary companion, it suppresses planet formation / survival. It looks like it's formation by 2/3, give or take. But there are all those planets out there that Kepler found are still out there. They're just around the rest of the stars. But this gives us a hint, especially when you tie it back to the young star, that it looks like this happens early on, maybe at the very early stages of star formation, that planet formation is just shut off. But we have this open question that I don't have an answer to yet, but still working on. Thanks.